We're off to chapter 13, which is gases. So we're going to talk about gases, obviously, gas law, gas stoichiometry, and some other things in this chapter. So when we're talking about gases, we are obviously talking about the state of matter where pretty much everybody has broken apart from one another. They're flying around in a container in most cases. And really, as they fly around, they do sort of collide a lot of times the walls of the container as well. And it's really these number of collisions or how many collisions we have, which is really what we associate with gases, which is what causes the pressure that we associate with gases. So a lot of times, obviously, the more collisions that we have, the higher the pressure obviously will become. And obviously, the lower the number of collisions, less the pressure will be. So when we talk about sort of gases, it's good to talk about sort of things that, are maybe normally found as gases and some things that maybe are not. When we talk about sort of normal conditions, these are usually like kind of table conditions, like you look up things in tables and stuff like that. And usually standard conditions basically sort of represents a temperature here of kind of 25 degrees Celsius and a pressure of about 1 atmosphere. An ATM is a unit of pressure, which is an atmosphere. And under these sort of normal sort of conditions, ionic compounds really do not typically exist as gases under normal conditions. And that's because, as we know, a ionic compound is basically made up of a cation, which is positively charged, and our anion, which is negatively charged. And basically what holds those guys together, as we talked about, is that electrostatic attraction, so that opposites attract. And that electrostatic attraction is pretty much one of the strongest sort of attractions that you could get. It is what is referred to sometimes also as an intramolecular force. So that electrostatic attraction is an intramolecular force, basically means within the molecule. So that's the forces that basically holds intramolecular force is the force that holds basically one molecule together, basically, that keeps it from falling apart. And obviously that is going to be a relatively strong force. And ionic compounds, because of this, typically will not go into the gas phase. And we did some experiments probably along the way there at the beginning and stuff where you evaporated off the water, you're left with some solid in your evaporating dish and stuff like that. And pretty much you could heat the heck out of it, and an ionic solid before it will go into the gas phase will pretty much just start to melt rather than go into the gas phase because of that really strong sort of attractive forces. Now, molecular compounds or covalent compounds are a little different than sort of ionic compounds. There are some molecular compounds, which obviously are things that are going to be sharing electrons to hold themselves together. They're actually held together gases under normal conditions, things like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, CH4 is methane, which is an organic sort of gas. But a vast majority of molecular compounds do come, though, as liquids and solids. The major difference sort of between an ionic compound and a covalent compound or a molecular compound is it is usually rather easier to convert a covalent compound or molecular compound into a gas than it is an ionic compound. Prime example, something obviously that you are probably familiar with, is something like water. So when we have, say, a couple of water molecules together, oxygen is more negative as it's polar, right? And hydrogen is more positive on oxygen. So the attractive force between the positive hydrogen one and the negative oxygen another is actually what holds one water molecule together with another. This is what is referred to as hydrogen bonding in this case. And hydrogen bonding is an example of what is referred to as an intermolecular force. And an intermolecular force is the force that holds one entire molecule basically together with another. So an intermolecular force is one that holds this molecule together with another and keeps them together. If you took actually just one individual water molecule, the OH bond on both sides, those are intramolecular forces. the covalent bonding, just like ionic bonding, is an intramolecular force, is the force that basically holds the water molecule together. And we know just from the example what happens with water, that the intermolecular force is always weaker because it doesn't take a lot of effort, just some fire, right? And get to about 100 degrees. And what happens when you hit the boiling point of water is it is the bond between the molecules that actually breaks first, allowing this water molecule to go into the gas phase, this one to go into the gas phase. If it was opposite and the intramolecular forces were weaker, and if you heated them, these guys would break first and you would create hydrogen gas and oxygen gas when you're trying to make pasta, and it probably would not work out so well for you. So instead is the forces between the different water molecules that break apart, allowing them to go there. So always the intermolecular force, and we'll get into this a little bit more in a later chapter as well, but intermolecular forces are always much weaker than intramolecular forces, and that allows molecular compounds to go into something like, for example, methane here, which is a organic molecule. It's a nonpolar molecule, and nonpolar molecules are held together with other nonpolar molecules through an intermolecular force that's known as dispersion forces. And those are pretty much the weakest that you could have. And that's why if you think about some organic things that you might not know are organic, that are organic, like methane, propane, butane, those are all gases under normal conditions because they're basically held together by very, very weak forces. So it's very easy for them to go into the gas phase. If you ever go off and take organic at some point in your career, sorry, but if you do take organic at some point in your career, they usually throw you into a fume hood to work. And that is because a lot of organic things are very volatile. They're not held together very tightly, and they go into the gas phase very, very easily. And obviously you don't usually want to be working in an open area with a lot of those things. And they're also very flammable sometimes as well. So the general rule is pretty much the stronger the intermolecular force, the force that holds one molecule together with another, the less likely that you would sort of find those things as a gas. Obviously, the weaker the force, then it's a pretty good chance that they will kind of be in the gas phase. Some of the substances that we're familiar with and we've talked about that are gases, a lot of those diatomic molecules that are elements like hydrogen, nitrogen, oxygen, fluorine, and chlorine. Ozone, which is O3, is a gas. And then, of course, our group 8 there are helium, neon, argon, and so forth, which are monatomic, which means they come as ones, how they naturally sort of come. So here on the periodic table, pretty much our hydrogen, and then everybody in this range going to be sort of gases under normal conditions. It's a good idea to talk a little bit about the difference between two words that are sometimes used sort of interchangeably, but they are different. If we sort of refer to something as a gas, that is normally a substance that is found in the gas phase under normal conditions. And that's different than a vapor. A vapor is usually a substance that's a liquid or a solid under normal conditions, but has been converted into a gas. So for example, when we talk about water, we usually refer to it a lot of times as water vapor as opposed to water gas, because it just kind of sounds funny. I suppose water gas, but we refer to it as water vapor because under normal conditions, water is found as a liquid. And obviously when we convert it in there, why you had to go to the chart the other day and today to figure out the vapor pressure of water, which is basically what happens in these experiments that you're doing. You basically are collecting water along the way in the gas form. Because of the reaction that's taking place. So that's why you look up, for example, the vapor pressure of water, which is basically water over the liquid part of what you collected in those tubes. So one of the major components of air is actually nitrogen gas, followed by oxygen gas. And obviously, as we sort of transitions maybe above sea level and get higher in terms of elevation, we do see an effect on the pressure. Pressure starts to decrease as you go up. Also, right, why they pressurize planes as you fly in the air and stuff like that. Also can affect things like, boiling points and stuff like that. So depending on the altitude where you're at, you can maybe boil your egg a lot quicker than you could somewhere else. But one of the major things that we do look at in terms of gases, as I talked about, is pressure. And pressure, again, is really related to the number of collisions that's going to occur. One of the ways that we can measure pressure is through a barometer. And there's a picture of a barometer, but a traditional barometer used to be, in most cases, a pool of mercury. And it has sort of a tube on it as well. And as the atmospheric pressure exerts down on it, the mercury in the tube rises. Mercury, by the way, if you ever do see it, actually makes a reverse meniscus heading in that direction, actually points upwards. And we actually read it from the top when you do something like mercury. And they've taken it out of most schools, including this one. So we have the digital one in there, and we also have the one hanging on the wall there by the oven is another barometer in that lab room. There are some common units of pressure, and these are really the three sort of common units that we see a lot in chemistry. An atmosphere, a torr named after the guy who invented the barometer, and mmHg, which is millimeters of mercury. And that's because, again, barometers used to be made up of mercury, and pretty much on the side of the barometer was a ruler. And you can take the measurement in inches, centimeters, or a lot of times millimeters of mercury is a common way you would take the measurement. A torr and a millimeter of mercury are basically equivalent to each other. It's a 1-to-1 conversion. Which means if you need to convert between those, you just change the units. It's basically going to be the same number. But between an atmosphere, it's 760 millimeters of mercury and 760 torr. And that 760 is an important conversion factor there. And you do need to know those three right there. So if you have atmospheres and you want millimeters of mercury or torr, you're going to multiply by the 760. And if you have torr or millimeters of mercury, either one, which again is pretty much the same number, you're going to divide by the 760 to get to atmospheres. So definitely you need to know those. Obviously in the circle, 1 atmosphere is 760 torr, 760 millimeters of mercury. Those are very, very common units that we use, obviously a lot here in chemistry. There are other units that we will see here in a second that, we don't use maybe as much here in chemistry, but these are, I would say, definitely your big three in terms of units that come across a lot. Now, in certain cases, you may need to get the units to a proper unit. In other cases, you just need to make sure that everybody's in the same unit so they all cancel out correctly when you use sort of the formulas. So here's a much prettier picture of a barometer, a traditional one. And again, as you see, atmospheric pressure coming down. And again, you can kind of see our meniscus heading in the other direction. Some other units of pressure, pascals and kilopascals are used sometimes, but not a lot, I would say, definitely in chemistry. Other units, as you may be familiar with, like PSI, pounds per square inch, right? 14.7 in an atmosphere. A bar is another unit of pressure. It's like 101 bar equals an atmosphere. So those are some other units that you might come across along your journey. But again, like I said, that atmospheres, torr, and millimeters of mercury, probably the most common, definitely for this class, and probably even for 1A as well, I would think. So let's talk a little bit about some of these gas laws here, just to make sure. And when we deal with gas laws, there's really three sort of variables that we deal with: pressure, volume, or temperature. Those are sort of the three big variables that we oftentimes will see. And in some cases, we keep one constant and maybe vary the other. In some cases, we may vary them all. Now, Boyle, what he saw was he looked at the relationship between pressure and volume, and he kept constant temperature here. So this is a situation where we keep constant temperature. And basically what Boyle saw was when we adjust the volume of a gas, so when the volume of a gas, for example, goes down, What's going to happen is if we squeeze down the volume of a gas to a really small volume, that means the gas molecules pretty much have a very small area to fly around in. And what that's going to do is definitely increase the number of collisions that's going to happen, right? So, if we put everybody into a small closet as you move around, there's definitely going to be a lot more collisions than there would be out here in a bigger room. And that's what's going to happen with the gas molecules. So because of that small volume, as the gas molecules are flying around, there's going to be a lot more collisions that's going to happen. The result of that is we will then see an increase in the pressure. Now, the opposite will happen if we actually take the volume and we increase the volume. If we increase the volume, we now have a much larger area for the gas molecules to fly around in. It's going to take longer for collisions to occur, and the less collisions that are going to occur is going to result in the pressure actually dropping. So what we will see is the pressure will actually go down. So sort of as one goes up, the other will go down. And it's really important sometimes you're looking at these gas laws to understand sort of what happens. One goes up, one goes down. It can really be helpful when you're doing the calculations to make sure that your answer sort of makes sense. You didn't maybe mess up a number along the way. And that's basically what it says down here. Another interesting thing about Boyle's law is if you did an experiment where you took pressure and the corresponding volume measurements for a gas, no matter what pressure volume measurements that you took, as long as they're related to each other, when you multiply them together, they will always hit the same number. They will always hit this constant number, which is what the K stands for here. The K stands for what's known as the proportionality constant. Basically, any pressure volume numbers that are related to each other in a Boyle's law situation will always end up being the same number. The nice thing about that is it allows us to really use Boyle's law in a sort of before and after situation. And that gets us to really what we look at for Boyle's law, which is right there. Here again at constant temperature. We got P1 times V1 is equal to P2 times V2. Again, kind of a before and after situation here. In terms of units, the pressure on each side could be really any pressure unit that you want, as long, again, as they are the same unit, so they all cancel out when you do the calculation. And the same thing with the volume here. The volume could be any unit you like, as long as, again, they are the same units on both sides. So again, it may require you in certain cases to convert one of the values or not convert one of the values, but definitely you want to make sure everybody's in the same units here. And that's what we see on this graph here, which is our pressure versus volume relationship. Again, at a much smaller volume, we have a much higher pressure. When we kind of increase the volume, we see a good drop in terms of the pressure. Again, giving everybody a little bit more room to kind of fly around in. Any questions on that there? All right, so let's try one here. An inflated balloon is 0.55 liters at sea level, 1 atmosphere. It goes to 6.5 kilometers, where the pressure is 0.4. Assuming constant temperature, what will be the final volume of the balloon? Which would be our Boyle's law, which definitely would be the one that we would use here. But again, you will have more than one, obviously, to choose from as we go through this chapter. A good rule of thumb is to just pull out the information. So obviously we have a volume that is 0.55 liters. We have 1 atmosphere, which is a pressure. We have 6.5 kilometers, which is useless information in this problem. We have another pressure here that is 0.4 atmospheres, and we are looking for a volume. So again, you can kind of see Boyle's law there, and a lot of times if you just kind of pull out the information and label it, will kind of show you almost the gas law that you should probably be using when you're doing the problem. Does it really matter which ones you number, 1 and 2? It doesn't, but we'll just go with 1s for those, 2 for those. The only thing that matters is you keep the numbers together that go together. Obviously, you could call 1s and 2s. It doesn't really matter. In this case, our atmospheres are the same, so we don't have to do any conversion there. So we could just go P1 V1 is equal to P2 V2. We're going to send P2 to the other side by dividing it, and that will give us P1 V1 over P2 is equal to V2. Putting in our correct numbers here, 0.55 liters our volume here, which is 1 atmosphere. That's our pressure actually in our volume. There we go. And our pressure here on the bottom, 0.4 atmospheres. So atmospheres will cancel, going to leave us with liters as our unit. And that is going to get us a 1.4 liters in this particular case. Any questions? So once again, understanding that it all sort of makes sense. What we see in terms of the pressure down, and it's 5 liters, ended at 1.4. So we did the volume go up here. So again, it's a good way to kind of check. They do like T1 for T2 or V1 for V2, and they flip everybody around in the wrong sort of spots sometimes. Talk about Charles' law, and really these two dealt with a couple of different things. One dealt with volume and temperature holding constant pressure. The other one dealt with over here, gay-lussacs, kind of pressure and temperature holding volume constant. So these are two different sort of relationships, Charles' law, the gay-lussacs law. So we do get actually two equations to go with it. For Charles' law, it is V1 over T1 is equal to V2 over T2 for Charles' law. And again, here, this is at constant pressure. Gay-Lussac's law is P1 over T1 is equal to P2 over T2. And this is at constant volume. So let's talk about what's going to happen in each of these situations as we adjust, say, the temperature. Let's take a look at on the right-hand side here. So on the right-hand side, we have a constant volume, which means our gas is pretty much in a container where that volume is fixed. So it will not go up, it will not go down. Our gas molecules, no matter what the situation is pretty much trapped in that volume for our relationship on the right there. So as we increase the temperature here in our situation on the right, our gas molecules should start flying faster or slower if we increase the temperature. They should go faster if we increase temperature to gain more energy. As they gain more energy, they're going to start flying around a lot faster. Now, on the situation on the right where the volume is fixed, they're pretty much going to fly around in that same space, which means they're going to start moving around faster. And that's going to cause a lot more collisions, right? Because they're moving faster. We're going to see an increase in the collisions. And what we will also see then is an increase in the pressure. So in this situation, if you increase the temperature because they're moving faster, the volume is fixed. There's just almost so much space to travel pretty much. They're going to have more collisions and the pressure will increase. Now, if we do the opposite and we lower the temperature, when we lower the temperature, it's like taking out energy, which means our gas molecules are going to be flying around a lot slower. And again, they're still in that same volume, so they're moving that same volume a lot slower, which means, again, it's going to take longer for collisions to occur. And what we would start to see is less collisions, and the pressure actually will go down in this case. So in Gay-Lussac's law there on the right, because of the fixed volume, when we increase the temperature, we should see an increase in the pressure. And when we decrease the temperature, we should see the pressure start to go down. Any questions on that there? Now, when we look at Charles' law on the left, our volume is no longer fixed, which means we're in a container where, frankly, the volume could go up, or we could also kind of drop the volume down like a movable piston type of thing. You can kind of go up and down and kind of decrease or increase the volume of the container. Now, what happens here in this case is we do maintain constant pressure, and it's actually the volume that allows us to do that. So for example, if we increase the temperature here on the left, the same thing's going to happen. Our gas molecules are going to get enough energy. They're going to start flying around a lot faster, which, as we saw on the right there, if the volume stays the same, we will start to see the pressure go up. But in this case, we want to actually keep a constant pressure. So what happens is the volume needs to adjust. So the volume actually increases when you increase the temperature. What that does is it gives the gas molecules a lot more space to fly around in. And even though they're moving faster, it basically keeps the number of collisions relatively constant. So because it keeps the collisions relatively constant, that is how our pressure stays relatively constant. And we will see the volume adjust upwards in that case. Now, if we decrease the temperature, once again, our gas molecules will be flying around slower. And if the volume stayed the same like it did on the right there, we would start to see the pressure drop. So what happens in this case is the volume will actually get smaller in this case. So even though they're moving slower, those gas molecules will still be able to keep up the same amount of collisions in that smaller volume. And that is how it's able to maintain constant pressure. So in a Charles law situation, it's actually the volume and its ability to adjust, which is what allows basically the pressure to remain constant. Any questions on that there? So again, these are two really important relationships, going up, going up, going down, that again will help you as you do calculations to make sure hopefully you didn't maybe invert a number. Your answer hopefully makes sense. Now, when we talk about volume here and pressure in terms of the units, it really doesn't matter. They could be any units of volume or pressure, once again, as long as they are the same on both sides. But there was an important relationship that was seen by when we graph the volume versus the temperature for any gas that you like. You can take any of these gases and bring the line down to the temperature side, and the temperature will always hit the exact same spot, which is minus 273.15 degrees Celsius. 273.15 is the number that we use to do what? Convert to Kelvin. So Kelvin recognized this and said, well, if I want to convert this to Kelvin, or really the absolute temperature scale, I would add 273.15. That would give me 0 Kelvin, which is absolute zero. So the bad news or good news of that is pretty much any gas law that you have, if you have temperature, it needs to be in Kelvin. So you got to convert everybody to Kelvin when you're dealing with temperature. So if we look at our gas laws here, the temperature here and the temperature on this side has to be in Kelvin. And again, that's our Celsius plus a 273. And it also includes questions where you were, for example, given the temperature in Celsius and even asked to give the answer in Celsius. So sometimes people, when they see questions like that, go, well, they gave it to me in Celsius and they want the answer in Celsius, so I can leave it in Celsius. You cannot, you will not get the right answer. So you do have to convert it from Celsius, put it into the gas law, get the answer in Kelvin, and then go back and convert it to Celsius on the back end. So don't even think about it. It's a no brain situation. If it's temperature and it's a gas law, convert it to Kelvin before you put it into the gas law. Any questions on that there? Okay, so that is again basically what this says here. Make sure that we get everybody into Kelvin. And here's our Charles law and our gay-lussacs law there, basically. All right, let's take a look at one here, I think. In an experiment, 452 milliliters of a gas in a light bulb is heated from 22 to 187 degrees Celsius. What is the final volume? So see what you come up with here. Okay, let's take a look. So once again, I highly recommend, now we got a few to choose from. You kind of pull out the information. So obviously we have a volume that is 452 milliliters. We have a temperature that's 22 degrees Celsius. We got another temperature that's 187, and we are looking for a volume. So again, obviously no pressure. So this one wouldn't be no good. This one would be no good. And you could kind of almost see Charles' law sitting there as you kind of pull out the information. So sometimes very helpful to do so. It kind of helps you point you in the right direction. Now, in terms of units, we definitely, again, with our temperatures here, have to convert it to temperature to Kelvin. So we're going to add a 273 to each of these guys to do that. And when we do that, our 273 plus our 22 going to give us 295 Kelvin. And our 187, I think it was there, plus 273, going to give us 460 Kelvin. Now, in terms of the units of our volume, it doesn't really matter. It just means when we solve for volume, it will still be in milliliters at that point. This is going to be our V1 T1 is equal to V2 T2. In this case, we are solving for V2. As you may know, in a situation like this, when you move something across the equal sign, it ends up in the opposite location. Yeah. So when I want to move T2 to the other side, it ends up on top. Since it started on the bottom, we're basically multiplying T2 to both sides in this case. That would give us V1 T2 divided by T1 is equal to V2. Putting in our numbers correctly here, we got our 452 milliliters up on top. We got our T2, which should go up on top in Kelvin. And we have our T1, which should go on the bottom here. Kelvin and Kelvin will cancel, going to leave us in milliliters in this case. That's a 452 times a 460 divided by a 295er. We can go with 705 milliliters in this particular case. Any questions on that? So once again, pretty much if you need to move anybody to the opposite sides here, they just end up in opposite locations. This is a quick way to rearrange it. We're basically multiplying or dividing depending on what you're doing in that case. We also can make sure that it does make sense. Once again, if we looked at our temperature here, we see that our temperature went up. And again, in this Charles law situations, we should then see our volume go up as well. Started at 452, ended at 705. So again, it does make sense based on what we do know should happen in that situation. Any questions on that there? Okay. All right, so let's take a look at one more here to finish it out with here. Let's talk about our good friend Avogadro. He had a number, but he really wanted a gas law, right? So Avogadro, when we think of Avogadro, right, that is 6.022 times 10 to the 23 equals 1 mole. So not surprisingly, Avogadro's law involves moles. Avogadro's law happens at a specific situation. It's actually constant temperature and pressure. So under constant temperature and pressure conditions, we get this relationship here, which is Avogadro's law. And that is V1 over N1 equals V2 over N2. N is the number of moles of the gas. So N is the number of moles of that gas. And you basically can use it like obviously any type of gas law there, kind of plug and chug into there. Sulfur or volume are the moles in this situation. It also is very helpful in stoichiometry that we'll talk about a little bit later on in this chapter, that you could kind of do a volume to volume relationship if it's constant temperature and pressure, very much like how you do a mole to mole relationship in stoichiometry. So it actually can allow you not to have to necessarily use a gas law to solve a stoichiometry problem. You could actually do almost a volume to volume relationship if it is constant temperature and pressure. So what we will see though is if we put all these guys together, our Charles law, Boyles law, and Avogadro's law, we get the granddaddy of them all, which is the ideal gas law. The ideal gas law is PV is equal to nRT. It is different in a couple of sense. First off, there is like no before and after situation. So there's kind of one pressure, one temperature, one volume. The other thing that is really important with the ideal gas law is it is really the most specific in terms of units. So when you use the ideal gas law, everybody has to be in specific units. The pressure when you use the ideal gas law has to be in the units of atmospheres. The volume has to be in units of liters. N has to be in units of moles, which is what it should be. And T has to be in units of Kelvin. And really the reason why all those guys has to be in those units is actually R, which is the gas constant. And this is a value that you always have. And the gas constant is 0.08206. And it has units of liters times atmosphere divided by Kelvin times mole. Now, some people nowadays round this number to 0.0821. You could use either number you like. I use the top one because that's what they beat in my head and I can't get it out. But a lot of books and stuff will use the 0.0821 number now. You can use either one, it should come out the same. The good news is, if you remember R, you can look at the units there and it pretty much will tell you what everybody else needs to be in terms of units when you use that. So definitely everybody's got to be in very specific units for an ideal gas law. An ideal gas law deals with an ideal gas, and what makes something an ideal gas is a couple of things. Under our normal conditions, we assume that the gas volume itself is negligible. So when you look at a lot of gas problems, you might not notice, but what they actually talk about in terms of the volume of the gas is actually the volume of the container. So when we think of an ideal situation, really the volume of the container is more important than the volume of the gas molecule itself. The other really major thing that makes something an ideal gas, and we'll talk a little bit more about it later on in this chapter, is the idea that in an ideal situation, you could have multiple gases together and they pretty much will not interact with each other. So there'll be no attractive forces between the two gases. There'll be no repulsive forces between the two gases. It's almost like the gases would be in there by themselves. So even though they're together in an ideal situation, they're almost like in there by themselves, and there's no sort of interaction between the different gases. Couple last important things here, which as we might have touched upon last time in lab, is the idea of what's known as STP. STP is standard temperature and pressure, and standard temperature and pressure does give you values. So when it's at STP, that means the temperature is 3 Kelvin or 60 torr or millimeters of mercury. So sometimes the problem, people go, they didn't give me anything like temperature or pressure, that STP, those are the values that you could use. You could put it into the ideal gas law and, and use it as you need. They really, it's related which at STP conditions and only at STP conditions, 1 mole of any gas will equal 22.414 liters. So this is actually a conversion factor that you could use when it's under standard temperature and pressure that will allow you not to have to use the ideal gas law. So this is kind of a quick conversion way that you could do it. The good news is you can use the ideal gas law in any situation, STP situation, non-STP situation. You could always use the ideal gas law. And frankly, you never have to use this conversion ever. You could just use the ideal gas law and put it in there. But if it is at STP conditions, you could use that. Could kind of save you a little bit of time of using the ideal gas law. But again, you should never use that conversion if it's not STP conditions. So it always has to be STP conditions. Any questions on that there? All right, we